Hi, my name is Hamid, and we're going to discuss how replication can be kept healthy. It's a challenge, pretty difficult one, but let's see. Um, just a bit about myself. I don't have a tattoo of Postgres anywhere. Um, I've been involved with the Postgres project for more than 15 years now. In different capacities, I've worked with different organizations, with EDB, with HiGo, Percona, and now with PG Edge. There was a time when I was responsible for releasing the official Postgres installers on all supported platforms, which were pretty hard at times with working with different operating systems and architectures. More recently, I'm working on an extension for an active-active replication solution, Spark, with PG Edge. Prior to that, I've contributed to PGTDE, which is being worked on by Percona. PGStat Monitor is an observability extension that's kind of like a big brother to PGStat Monitor, and it offers more features, and actually it caters for the deficiencies of PGStat statements where the observability challenges come up in its statistical data. So here's what to expect. We're just going to take it gradually and go through replication and how we then look into the conflicts in replication. So we'll start with MVCC and see how that plays a pivotal role in causing replication conflicts. We'll move to streaming replication then, and then the conflicts in streaming replication, moving on to logical replication after that, and see what kind of challenges we face up with logical replication, and finally, how those challenges can be then solved with Spark. That's an extension that we're working on and we believe has come of age recently with a lot of changes been done in it. So I think the first question to ask is, why do we need MVCC? So MVCC is essentially there for multiple reasons. One is that it allows multiple users, multiple transactions to run at the same time without blocking one another. So reads would not block reads, reads should not block writes, and we just want a smooth operation of the database system where multiple activities can happen simultaneously without blocking one another. So internally, what happens is that Postgres is going to maintain a multiple version. So it's going to maintain different versions as you make changes to rows and data. So each backend, as it makes changes, is going to have a new version of that row. And that's the way Postgres manages it. It needs to know actually when it's making those changes, it needs to know about the visibility of those changes. It needs to know the visibility of the changes that it should see. So there are snapshots. Snapshots are really, it's nothing, it's just a couple of lists which are the two values, which one defines the transactions that have gone before itself. So anything that has happened in the past, then you have the transactions that will happen in the future, and you'll have a list of currently running transactions. So that's its way of identifying its visibility to different data or rows or tuples that it wants to access. So really at the core of it is to optimize reads and not block the writes. So it's done through a detailed locking mechanism. The side effect of this is that you'll end up with bloating. That's a typical issue when Postgres, when you have data getting bloated over a period of time. You have tables that are going beyond a significant size, more than the data itself that's valid in the table or the indexes. So it causes a lot of challenges, but it does have benefits in terms of how it parallelizes the access to data. So the thing about multi-version is that we need a way of identifying transactions, and comes in transaction ID. That's a 32-bit integer that is basically keeping track of your position in the timeline, so to speak. It's not precisely that, but it's more about an identifier of the transaction that's currently occurring. So you are assigned a transaction ID once you start making changes to the data. Before that, there is no transaction ID assigned. So as long as you're doing a read, you don't have a public transaction ID assigned. You'll have a transaction ID assigned, but that's local to your backend. Nothing that's public. So the moment you make the first change is when you're assigned a transaction ID. This transaction ID is the one that is then, as I discussed in the snapshot, so this is the transaction ID that other running transactions will see, maybe in their snapshots, maybe if you've committed, would see them as a past transaction or as a future transaction for some. So with data, you need to obviously control how you access it. Postgres does it in different ways. There are different types of data internally that Postgres has to manage. From a user perspective, you have user logs, you can have advisory logs, you have explicit logs. But internally, Postgres server manages 3 different types of logs. You have spin logs. Spin logs are really for quick access. You are meant to hold that log for a very, very brief duration, maybe say increment a value, check or test a value, and that's pretty much it. It's more for atomic operations. It's not for any long running function calls where you want to hold a spin lock. It's busy waiting. So while you're holding this lock, others would be busy waiting. So you're not meant to hold this for long periods. Then you have lightweight locks. These are really at the core of the whole Postgres, and these are how you protect larger data structures in Postgres. And finally, you have regular locks. So what you do not have with other locks and you have with regular locks is deadlock detection. Deadlock detection comes in with regular locks. Spin locks don't have it, lightweight locks don't have it. But when you look at regular locks, internally they're implemented through lightweight locks, and it goes through a whole procedure of acquiring those locks or waiting on those locks, or maybe then identifying a cycle and goes through a deadlock detection process. So those are implemented through this. So why am I touching all of this? So when we look at a tuple structure, there are hidden columns, there are hidden metadata that a tuple has that we need to remember. It has quite a few details other than the tuple data itself. The tuple data obviously would be significantly larger, but still we'll have the xmin, the xmax. That's the minimum. The xmin really refers to the transaction ID that created this tuple, and xmax refers to the transaction ID that deleted this tuple or updated this, or where you have a new version of this tuple. Xmax does not always refer to a valid transaction ID. A transaction that have updated this tuple and aborted might leave a valid Xmax for this tuple, but it's going to mention some of that detail in the info mask, where it's going to mention about the visibility, whether the Xmax is valid or not, which then defines the visibility of this tuple. So if you have a transaction, if you have xmin, obviously with any tuple that's created, you'll have a valid xmin. And then in some cases you might not. With an inserted tuple that's aborted, you might not even have a valid xmin. But say you have a valid inserted tuple, and then you have a transaction that comes in that deletes it, but aborts the transaction. As it deletes it, it acquires a lock on this tuple. It's going to have its own transaction ID in Xmax. So its XID will be in Xmax, and it will also just lock this transaction so nobody else can while it's updating it. So that's how it's ensuring that concurrency is managed and the updates to the same data are basically managed by a way of lock system. So in comes streaming replication. So I'm just building up to the components of how replication and all of these different components basically feed into the replication conflicts for streaming replication and logical replication later on. Write-ahead log was introduced in 7.1 very early on, 2001. Before that, every commit was essentially writing the data page to disk, which meant that it was causing all kind of challenges with inconsistencies, with partial writes, with whatnot, and the performance obviously was pretty horrible. There were essentially two options whether when you want to talk about crash recovery, either you have a wall, a write-ahead log, or you have shadow copy. Shadow copies are when you maintain a copy of the data pages separately as you make those changes, and you maintain a list of valid data pages. And finally, when a transaction commits, you replace the root of that chain to point to your valid chain now. The benefit of shadow copy is that you never need to recover. You always have correct, up-to-date data. You don't have partial writes. You don't have uncommitted transactions. You don't have in-progress transaction data. With write-ahead log, basically, you're writing to a wall stream. So all the changes are going into a wall stream before they make their way to a page. So tables are not updated immediately. Wall is what ensures persistence on disk first. So it's durability and consistency. That's what wall is assuring. Implementation of this actually then obviously also optimize the performance, because now you have just one process that's writing to disk. You have a smaller footprint that's being written per transaction, so it becomes much simpler now. The other thing to remember about wall is that the transactions are interleaved. So you have one transaction that started writing something, so it inserted a transaction. It has not committed yet. Another transaction comes in. It will write something as well. So it's basically the transactions would be interleaved. They're not going to be like one transaction then followed by another transaction, not necessarily in that way. So replication in Postgres evolved over time. The first component of that streaming replication was wall. It was followed by warm standby lock shipping, where the chunks or the wall segments were being shipped out as a package. The challenge with this was that this was asynchronous and you still could have data loss. You had your timeouts, you have your thresholds for how much wall data you can maintain, but still there was that possibility that you can always end up losing that much data that's not been sent over. 2010, 9.0, you had your hot standbys. With hot standbys, you have two core processes that came in. You had wall sender and wall receiver process. Now, these are critical in streaming replication or in replication in general, wall sender in particular. The responsibilities was not just about picking up the data for wall sender, sending it out, but for wall receiver, it was also about writing that data, flushing that data to disk, and then just basically pinging the startup process to start applying those wall changes. Logical decoding and logical replication came in 9.4. So this is very different to how streaming replication works. Streaming replication has three core processes. You have your startup and wall receiver. You have the wall sender. Wall receiver and startup on the standby server, the responsibilities are really wall receiver is going to ensure that the wall that it receives from the wall receiver is basically going to be flushed onto the disk. The strategy of how it confirms that really depends on the confirmation or your synchronous commit, basically GUC. Startup was an old process. Its responsibility is really to recover. So even after a crash or a server crash, your startup process will take up any wall records, and it's going to apply those until it reaches a consistent state. So you have these three working together where the connection gets established by walls. So the connection is basically started by wall receiver. Wall receiver initiates a connection request. Since it has connection information, it's going to send that connection information or it's going to attempt to connect to the primary server. The primary server is going to spawn a wall sender process, which is then going to establish a TCP connection with wall receiver, and then you have a connection established between the two. As the transactions commit, there are a couple of functions that basically essentially ensure that wall data is written is xlog insert and xlog flush. These are the two core functions that are responsible for ensuring or flushing xlog data to disk. When this happens, wall senders are woken up. So when you're writing a wall, basically a wall record, you signal wall sender process, and the wall senders wake up and they start then processing that data and send out that data to wall receiver. They wait for different acknowledgements. There are 3 different kind of acknowledgements that a wall receiver, wall sender would wait for, possibly, depending on, again, your configuration. The first one is whether the data has been received or written. The next is whether the data has been flushed on the standby. And the third one is whether the data has been applied. These are the 3 LSNs, log sequence numbers, which the standby would be reporting back to the primary server. As a transaction commits, it's going to wait for those confirmations. It waits on, basically just sleeps on a particular function during commit transaction processing. In between, to ensure that the communication is healthy, you have a heartbeat where wall sender and wall receiver are basically sending back and forth to ensure that they're aware of one another. Internally, what happens are the functions that are responsible for applying wall. They're really dependent on the access method, so you'll have a standby redo function or a heap redo function, and those are really, similarly, you have redo functions for other access methods as well. But with each, there are 2 different kind of conflicts that we're going to look at for streaming replication. The first one with standby redo is locks. Overall, when we look at conflicts in streaming replication, there are 5 different types of conflicts. Categorizing them in different categories. Table space is when a table space is dropped or a database is dropped, is when you'll have a conflict on the standby server about a resource that is no longer available to it. Snapshot is when the corresponding row versions are not available. Remember that for MVCC actually ends up creating different row versions. So based on your transaction ID, you will have access to some row versions and you might not be able to see other row versions. So if your corresponding row version is no longer available, you would have an issue and a conflict there. Deadlock and buffer pins are others. Sorry, yeah, so there's only effectively one view in Postgres in the statistics collector, and that's pgstat database conflicts, and that is essentially a counter of each conflict per database. So you'll have one counter for all of these conflict types per database, which does not really give you a lot of information into why this conflict happened, what could have been done to avoid it. You have one other field in pgstat database, but that's again just one field, nothing too informative. To generate a lock conflict, it's actually pretty easy. You start, say, in this particular example, you create a table, fill it with some data. On the standby, you start a transaction as well, and then you access that table. On the primary, you drop that table. Now, what happens is that in streaming replication, you have a wall receiver process. The wall receiver process has a core responsibility of ensuring that it's not lagging too far behind in the wall stream. So it needs to apply those changes, it needs to receive and get those changes applied. It cannot wait for other transactions forever. So it obviously takes priority over other transactions. So it does have a configurable parameter which is max standby streaming delay, which it waits on. By default, it's 30 seconds, I believe. So it's going to wait for that much, and then it's going to effectively kill all of those transactions that are holding those locks. The way, actually internally how it's done is that when on the primary side, when we're running a transaction and we're acquiring exclusive locks, we're actually then also registering those locks in the wall. So the wall gets a kind of a complete list of exclusive locks that need to be acquired to process this transaction. When the transaction commits, that record comes over and we need to apply it on the standby. We start with all the list of exclusive locks that we know are required to apply this transaction. So immediately, the server, the standby redo function, is going to attempt and it's going to acquire all of those exclusive locks. Now, those exclusive locks are actually implemented through lightweight locks. So LW locks in exclusive mode must be acquired. So the moment it's unable to acquire one of those locks is when it's going to wait for this, and then it's essentially going to retry and see after the timeout, it's going to retry and see whether it can acquire that lock again. It knows which processes are actually holding those locks. So if by that time those processes have not released those locks, it's going to kill all of those with a specific signal. And that's when you see this conflict in the log. And pgstat database conflicts gets a value incremented for conf lock field. So yeah, this is pretty much what I just explained. With standby redo, it's going to attempt all those lock acquisitions, and then it's going to fail immediately. It hasn't done any other processing yet. Snapshot conflicts are slightly different. They're essentially triggered by vacuum or hot chain pruning. On the primary side, you have a table. On the standby side, you are trying to access row versions. You could do it with a long-running query that runs for hours, but this is, for example purposes, this is a very easy way of implementing, even with smaller data sets, that you define a cursor, declare a cursor, and you fetch that data from there. So the moment you delete data and you vacuum it, it now needs to do the same vacuuming operation on the standby side. I think maybe in version 16 or 17, they've changed that manual vacuum now also honors the timeout for standby. Previously, when you do a manual vacuum, it pretty much immediately triggers the conflict on the standby side. So the moment you have vacuumed, the wall receiver has received and it needs to do certain operations. A vacuuming is a heap operation, and it needs to basically prune old row versions. So for it to be able to prune those versions, it needs to acquire exclusive locks. And those locks cannot be granted since another transaction is holding a read-only lock on it. So it cannot have an exclusive lock on that tuple. So when it runs out of time, it is going to then obviously not be very happy and end up killing all of those. The challenge with monitoring these is that there's not a lot of information, and all of these are localized to the standbys. So on each standby, you have one row per database where all of these conflicts or different type of conflicts are registered or incremented But again, there is not much observability in terms of how those conflicts were originated, whether there were queries that particularly caused that conflict, and how you can actually solve that. So there are options when you can increase that visibility. One is to ensure that you have query ID as part of your log. Query ID was introduced in version 14, and the GUC is compute query ID. Prior to this, there wasn't a query ID. It was essentially part of pgstat statements, which used to, for its own observability information, used to compute the query ID for itself. So version 14, it comes by default, it's auto, so it's neither on nor off. The auto setting enables any of the tools like pgstat monitor or stat statements to enable query ID computation. Query ID computation is a little, it's obviously going to use certain CPU cycles. It uses OIDs of objects to calculate a query ID. So it's predictable. It's the same query ID in terms of streaming replication. It will be identical on the primary and the standby side. So same query ID will result in the same query will result in the same query ID. You can also log for recovery conflict waits and see whether it's going beyond deadlock timeout, to see whether it's waiting more than it should have for acquiring those locks. So that's another way of you looking into whether you can possibly avoid this or identify a pattern with these. Long-running queries, obviously long-running queries or often prepared transactions or prepared transactions can hold back these locks for a longer duration. At times you cannot see a lot of those details about query IDs or the originating application of a query. So pgstat monitor actually does solve that problem, and you might want to look at it, to look into long-running queries and see whether you can identify the application or the particular query or the parameters of that query and their values. pgstat statements would not show you the parameter values of a query. Finally, you might want to consider rewriting queries. Even a read access to a query, to a table or a tuple would cause a conflict because it would prevent an exclusive lock. So whether you actually need to touch those tuples, that's an option to consider. There are a couple of parameters that you obviously are simple and easy to remember. You have the standby archive delay and you have standby delay, streaming delay. They serve different purpose. Archive is essentially for recovery. Streaming is when you're streaming the transaction and processing that stream of wall data. Hot standby feedback is a way or is a mechanism of informing the primary that standby is working on certain XIDs and the corresponding tuples should not be vacuumed out or should not be pruned. The problem with this is that what if the standby disconnects for a while and the information is not passed on? So logical replication actually solves these problems in a different way. It has its benefits, it has its challenges. Logical replication is not a block-based replication. It does not go byte by byte. It does not have block addresses. It's essentially data. It's essentially changes to that data that needs to be shared with another Postgres server. So you have a publisher, you have a subscriber, and you can go either in binary mode or in text mode. The difference is that when you go into a binary mode, it's obviously faster, it's more optimized, but the benefits of having in a text mode is that you can do logical replication completely agnostic of the underlying hardware architecture, or you can go through different major versions. You can also have implicit typecast. So a tiny int on the primary on the publisher could actually be a big int on the subscriber. So you can have that benefit with text mode and logical replication. So logical replication is going to ship out tuple data. It's going to pick up that information and it's going to send it packaged in a message, in a protocol messaging setup. The challenge with it is that inserts are fine. Inserts would not conflict. But when you have an update or a delete, that update or delete requires the subscriber to identify the tuple in its data, the corresponding tuple. So it needs to know which tuple it needs to update, which tuple it needs to delete. And that's where the concept of replica identity comes in. By default, it's just your primary key, but you can also set it to full, and then you can have a full scale update and delete mechanisms. Logical replication, the native does not do sequences. It will share the data of sequences, but it's not going to change or update the catalogs. So the standby and so the subscriber and the publishers obviously will have the same data, but their starting position or the current position of the sequence numbers would be different. And it does not do large objects. It does do toast, but not large objects. Similar to streaming replication, it has three processes. You have the apply workers, and you have the logical replication launcher, and you have vault sender. Vault sender is responsible for sending out the logical message with the data, and the apply worker is responsible for applying that change. The connection is again established by the apply worker. The apply worker, when it starts, is going to send out start replication command, and that's when the publisher will spawn a vault sender, and the vault sender will establish a connection with the apply worker. So logical decoding is the concept of decoding that transaction from the wall into more textual format that can be then interpreted. It's more of an infrastructure where it allows us to write extensions, it allows us to write decoders or output plugins, which can then process it in any way that they wish. So they'll receive that transaction. It starts with when you commit a transaction. So this will not be invoked, this process would not be invoked if you have an aborted transaction. So only when a transaction commits. So that's simple. So there's no noise here. So the moment we have a transaction that's committed, we begin to decode that transaction, we identify the changes in it, and we send all of those to the subscribers. Finally, we'll end up sending a commit message to let the subscriber know that this was the last message for this particular transaction. There are replication slots, which are logical and your streaming replication slots. They're different in nature and how they process. The challenge with logical replication slots versus the streaming replication slots is that streaming replication slots will carry data for log sequence numbers to ensure that the wall is retained and the wall segments are not recycled. But it will also, as part of its messaging or a part of its communication with the wall sender, it will also send out X-mens that it still needs to see. So it will basically define X-men horizons as well. With logical, since you have possibly two active servers, there is no X-men. So all it has is the knowledge of the wall that it has received, the changes to the point in the wall that it has received, not anything about the X-mens, which means that vacuuming and hot chain pruning can happen. And if you want to ensure that those do not happen, you will have to hack the internal core Postgres server to do so. Logical decoding provides an API interface, looks something like this, and as you can see, there are a lot of functions. The functions essentially handle your prepared transactions, your streaming transactions, your begin transactions, your row filters for origin, etc. So not going to go into more detail into this. So conflicts in logical replication, they're essentially data conflicts. So you have an insert conflict, and this is critical. The information that you'll see in the log So you see that the first message is that a logical apply worker has started. So replication has started, and then what I did was I inserted the same primary key on both nodes. So I entered, or I committed a transaction with the same primary key on the subscriber as well as on the publisher. So I ended up having a duplicate key constraint violation. So what happens then? The apply worker has no control then. The moment it receives an exception, the moment it receives an issue, it essentially needs to throw an error and it needs to exit. But it does, before exiting, it does provide us with some information about the position in the wall where the transaction that it was processing finishes, which means that the next position in the wall would be pointing to, or would be of a different transaction. So, but the other important thing is to note in the brackets the numbers. Those are your PIDs. You start looking at 592, 592, 592, 592, 941. So 941 is your launcher. So that's your logical replication launcher. The first few messages are from the apply worker. By that time, the apply worker has exited, and that message is being broadcasted by, basically emitted by the launcher. And yeah, so next slide, next slide, next slide, that's the same. Yeah, what you'll notice is the first column changes, 57, 58, 59, and the time changes. The other important information to note is that from the time when you have a conflict and the time when you have another apply worker start, in this case, and in case you notice, this is a different slide. So this slide, and this slide deliberately kept the same slides, the same formatting. I'll let you know why. But if you look at that time here, it's 9 seconds, and this was 4 seconds. So apply worker restarted in 5 seconds, and this is on my laptop where there is no latency. So it took 5 seconds. Now imagine the number of transactions that might have happened on the publisher during these 5 seconds, the kind of workload you might have there, and the number of transactions that we need to reprocess here. So some transactions would have to be resent, some transactions would have to be reprocessed by the output plugin or the wall sender. So it's not just about running or having an issue here, it's also significantly impacting your performance. The more conflicts you end up having, the more restarts there will be, the more transmission of that data will be required. So all the transactions that might have been sent over those 5 seconds would have to be retransmitted. So if you continuously have this, you have a problem. But look at the line numbers on the first column, 52, 57. The reason why I actually put out the same file and the same information is that in the server log on the standby, it will carry on emitting this message. It will go on forever. So the server, Postgres, does not resolve this conflict. And it's going to fill up your log files. So it will carry on emitting. What happens is that your apply worker, once it has an error, it exits with an error code. It's relaunched. The same transaction is being processed again. It runs into the same issue again. It exits again and is restarted again. So it's a cycle that's never ending. And it's a cycle that actually shows in the log file then. The update in the native replication, there is actually no strategy. There is no strategy. So the transaction that comes in after the change will have its change updated into the table. It ignores the timestamps, so it's not the last wins, it's not the current one wins. It will just update that data, whichever comes later. It might have happened in an earlier time on a publisher as compared to the change here, or it might have happened later. It's completely ignored. So there is no timestamp management here. There is no conflict resolution of any sort. Then you have a delete-delete conflict. And actually, delete-delete conflict, although leads to a consistent state on both servers, it actually is an issue. It actually is a conflict. Because if we expect the replication to work properly, how can we delete the same row on two different servers? We expect that that delete will get replicated across, right? So when I delete it on the publisher, it should get deleted on the standby, on the subscriber as well. So if I have a delete that's happened on the standby, on the publisher and on the subscriber, both have deleted their data independently, and that information gets replicated, there's actually nothing written in the log. So Postgres does not inform you that something has screwed up, that a transaction that should have only come once has come to two different nodes and has made those changes, because then you wouldn't actually know when that change happened. So although they arrived at the same state of data, when they arrived and how they arrived is not known. So to categorize the data conflicts, we can identify or put them into 4 different categories. You have the non-divergent conflicts, where the state of the data is consistent at the end. So you'll have the same data on both publisher and subscriber with a delete-delete conflict. So both deletes happened on independently. You have an update-delete conflict. So an update happened and delete happened. What sequence doesn't matter, because if the update arrives later, it's not going to find that tuple. So it still end up going to have the same data on both sides. Then you have the divergent conflicts, where you can end up with different data on different nodes. So publisher and subscriber, or node 1 or node 2 could have different data. So if you have inserts on both, you can end up with primary key violation. Similarly with update. Which update do you want to honor? The first one or the second one, your local change, or the remote one? Then you have the sequencing one. So whether you have an update, an insert, if they arrive out of sequence, your update comes earlier. Say you have a more complex network with multiple active servers, there is a possibility that your update is routed through a different server earlier than the insert. Update is not going to find that tuple, and it's just going to completely get ignored. And the insert would come later through a different channel, and that is going to leave a different data behind. Similarly, a delete, insert and delete. What happens if a delete comes in first and an insert later? So you'll have a row that should not exist. So you have that possibility. And finally, you have phantom conflict, where the phantom conflict is when while you're processing and applying those changes on the subscriber, you want to inform your replication slot on the publisher that I have made this change. I have applied this change. But what happens if you actually crash before informing the publisher? It's going to resend that transaction, and you're going to reapply that, and yeah, it can have any kind of issues. So at PG Edge, we're working on Spock. This is kind of the next phase for PG Logical and based off BDR2. It's open source, so no strings attached. It does solve pretty much all of those problems that we've discussed with logical replication. It does come with a conflict-free replicated data type. This is for numeric data types. Spock does have a few minor patches to the core server, and those are available in the public Git repository. And I think maybe it's 100 lines, 150 lines, probably less. So very minimal changes to the server core, and where it's essentially just plugging in a few minor attributes where we need them, or making changes to certain elements in Postgres. So it has a delta apply functionality, which basically is a conflict-free, conflict avoidance strategy. You'll never have a conflict with delta apply data types. The other option is, the second thing is that when it's going to apply an update or a delete, it's actually going to look up whether the relevant row or tuple is available, whether it can find it in its local data. So it's going to wait there. It does have conflict resolution, so it can resolve certain conflicts based on timestamps, based on strategies that we define. And it does have exception logs and resolution logs to let you know whether something that should not happen has happened, but it's going to provide you with ample details to be able to debug that and make sure that you can trace it down. So pretty much consistent state of database is ensured here. It does have commit ordering. We do have an implementation of a Lamport clock, which is kind of a logical clock that ensures sequencing of transactions. It does address phantom commit avoidance. That is through a state machine, pretty much, that we've implemented. It uses Snowflake sequences with an identifier, node identifier as part of it. And we do have DDL replication. So when you alter a column or you add a new table or you make changes, it does replicate that information. This is how delta apply works. So essentially, delta apply avoids conflicts by taking the old value and the new value of a column, taking the differential of that and applying that change. So if you look at node 1, it has a value of 300, and it wants to update it to 310. That's a delta of 10. On node 2, we're adding 5. So the new value is 305. But as that transaction gets replicated, the node 2 also has the same value, and node 1 will get the same value with the transaction going back to node 1. So both node 1 and node 2 will end up with 315. There is no conflict. It's a conflict-free replicated data type. We have what we prefer is last update wins. So we don't care about the first update. We don't like local change wins or remote change wins. What we're looking at is last update wins. So in this particular case, you see that once you start a transaction on one node and you do a transaction on the other node in the meantime, now you basically have a conflict here, and that conflict is then registered in a conflict table. In this particular case, you have a resolution because it all gets resolved to a consistent value on both nodes. So you have a resolution which informs you that what has changed and the details. So data conflicts, we're capturing them in exception logs. So non-divergent conflicts, we have exception logs. For divergent conflicts, we have exception logs, and we have numeric fields which are handled through a delta apply. We have commit ordering, which ensures that we do not have sequencing issues from one origin. We do have the phantom conflicts is avoided because we're maintaining a progress state on the subscriber side to ensure and to understand where we are at in context of the publisher. So that problem, if we crash before actually informing the publisher, can never happen because we know what to discard on this side. And that's all. Thank you.
Okay, we do have a couple minutes for questions. Got any out there?
I think I just poured them.
Awesome. All right, guys. How about if we could